Hello and welcome back. Today, we're going to make a function spin and maybe I'm going to make your head spin too, as we find the volume of a three-dimensional solid formed by rotating a curve or curves around a set of axes. We've used integration to evaluate areas of regions. If a region in a plane is revolved about a line, the resulting solid is a solid of revolution, and the line is called the axis of revolution. Consider this region R bounded by the x-axis, the y-axis, and the line y equals negative 1/3 x plus 2. Now imagine rotating region R about the x-axis 360 degrees. Let me show you what would happen here. I'm going to rotate it. Wow, look at that. Okay, now let me spin this so you can see. We ended up with a cone. Now, we know the volume of a cone from geometry is 1/3 pi r squared h. The radius of our cone is, it's the height of the function right there, the radius of the base, and the height is 6. There's the height of the cone right there. So we can calculate the volume to be 8 pi units cubed. Okay, cool. Now, let's do this again, but this time we're going to find the volume using calculus. So to do that, I'm going to take just a small little slice of that region and rotate just it around the x-axis. And when I do that, let me show you what this looks like. It creates a little disc. And that disc can be anywhere on the x-axis. If I move it all the way to the back, I can start adding and adding like an infinite number of discs. And look what I've created. I've got my cone again. Let's slow that down and figure out how calculus can be involved in this. I took that tiny little slice of the region and rotated just it around the x-axis. And when I did that, what I created was actually a really thin cylinder. And I know that the volume of a cylinder, from geometry, is pi r squared times the height. And for us, the radius of that cylinder is just the height of the function anywhere on that interval. And the height of the cylinder is however wide it is, the change in x, or dx. So the volume of that little cylinder right there, we've got pi, and then r squared times the height. Okay, so my r, again, is the height of the function, and the dx, that's the height right there. Now, if I want the whole cone, I just need that infinite number of discs from 0 to 6. So I just integrate that. And if you evaluate it, you get 8 pi units cubed again. So of course this begs the question, why not just use the geometry formulas? Well, we don't always have a known formula. We call this the disk method, and you can rotate functions around the x-axis, the y-axis, or anything parallel to those. So let's say you take a function and rotate it around the x-axis or any line parallel to the x-axis, then you would use this equation here, which is what we just did. We've got pi times the radius squared times the height, integrated over whatever interval we need. And we're solving for y in terms of x, so we are dxing that. Now, we can also rotate it around the y-axis or anything parallel to the y-axis. And the function is the same, except for we're solving for y in terms of x. There's going to be a dy at the end of that. Let's try another one. A region R is created by the x-axis, x equals 0, x equals 4, and y equals sine x. Find the volume of the solid created by rotating R around the x-axis. So we're going to have a dx involved in this. So again, I'm going to take a little slice of the function and rotate just it to create a cylinder. Now let's take a look at what this is going to look like. Let me show you. I'm going to rotate just the whole function right now. There we go. Whoa. Look it, I got like a fish. It's like a sine fish. And we don't have a volume of that in geometry. So we're going to have to use calculus to find this. Again, the volume of that little cylinder is pi r squared times the height. And r, in this case, the radius of that little cylinder, is the function sine of x. So here we go. It's pi, and then r squared times the height, and we're integrating that from 0 to 4 to find the volume of my little sine fish there. And you can plug that into your calculator, and it's 5.506 units cubed. Let's try one around the y-axis. So here we have another region, and it's created by the x-axis, y equals 5 and y equals x squared. So let's find the volume of this by rotating around the y-axis. Same thing though, I take just a little slice and rotate it. And the radius of that cylinder that I've created is the height of the function. It's just that the height of the function now starts at the y-axis and goes out that way. And so I can plug that into the volume of my cylinder. So I've got pi r squared, in this case r is square root of y, and then just throw that into the formula. Now we can do this one by hand. I'll do this one a little bit quick. So let's see, add 1, divide by it to integrate y, and then evaluate that from 0 to 5, and you get 25 pi over 2 units cubed. This one is super cool. Find an integral expression, so we don't have to solve it, for the volume of the solid generated when the region between the graphs of f of x, that's the blue line, and g of x, that's the red line, from 0 to 5 is revolved around the x-axis. So we're going to have a little slice of just that region between those two functions and rotate it around the x-axis. So what do we get here? We have a disk, but it's got a hole in the middle. And if we move that disk back and start adding like an infinite number of disks, what do we end up with? We have a solid with a hole in the middle. So what do we do about that? We're going to start by just pretending that that red line's not there for a second. And we'll find the area of the region, we're going to rotate just the blue line around, okay? And when we do that, we get pi r squared times the height. But I'm going to call that r squared big R, because that's the big part of the area. And then what I need to do is I need to subtract the little stuff in here. I need to subtract this whole area that's here. So I'll call that little r and just take it out. So I've got pi and then big R squared minus little r squared. This is called the washer method because, well, sometimes there's a hole in the solid. Rotating a slice of the solid will create a washer with an outer radius, big R, and an inner radius, little r. The formulas for these are, well, very similar. We have big R squared minus little r squared. That's parallel to the x-axis. Notice and this is important, the functions are squared before subtracting. So what you don't want is big R minus little r squared. Don't do that. And of course, we can do it around the y-axis as well. Okay, so we're going to find the volume of the solid formed by the region bounded by the graphs of y equals the square root of x and y equals x squared. Ooh, when the region is revolved around the y-axis. So we're going to have our big R, and we're going to have a little r. But because we're going around the y-axis, we need to solve for x so that it's in terms of y. So y equals x squared is going to be x equals the square root of y. So that's the height, that's that big R right there, going from the y-axis all the way to the blue function. And then y equals the square root of x becomes x equals y squared. And then we can throw it into our formula. So we've got pi on the outside, and then big R squared minus little r squared times the height on the inside. Well, that's a crazy looking h, isn't it? Okay, and then we can just clean that up a little bit and add 1, divide by it, evaluate from 0 to 1, and we have 3 pi over 10 units cubed. Here we have a solid plastic sphere of radius 5 inches, and it's going to have a hole bored out of the center with a radius of 3 inches. So what is the volume of the resulting plastic sphere? They didn't give us any functions or equations to work with, so we know that this circle right here, the top of that, well, it's a circle, I just said that. That's a terrible circle. The equation for that is x squared plus y squared equals 25. And if I solve for y, I can just get the top half, just the top half right here, okay? That's the square root of 25 minus x squared. And again, I can just take a little bit of it, take a slice. We've got a big R, and then the hole that we're creating is a little r. Let's see what this is going to look like. There's my washer. Okay, move it to the back, and then add an infinite amount of washers. Hey, that's kind of cool, isn't it? Look at that. Looks kind of like an eyeball. We'll rotate it so you can see it. Oh, there's the inside. All right, so shall we set this up? Here we've got pi, and then big R squared minus, and then little r is just a constant height of 3, so there's little r squared dx because we're rotating around the x-axis, and plug that into your calculator, and we've got 268.0825. Uh-oh, I need to write here units cubed. Don't forget to label your answers. Okay, so hopefully your head is spinning a little bit, because this is so cool how we can spin functions to create solids. Thanks for being here.